my turn camera on, turn audio on. Can anybody hear me?
Yeah, I can hear you.
Perfect. Thank you. Just always need a confirmation just to make sure that I'm not talking to myself. Anyway, so let's start off. I'll give you a little bit of an idea. We'll talk a little bit about your final exam first. Then the remaining week that we have. So that's number 2 that I'm looking at. So that's the second thing that I'll talk about. Following that, we will start off with the last component that we have, which is regression, which is what we are going to work with today. Regression is something that follows you around for your entire life if you are planning to be a market researcher. Obviously, what we start off with today is a little simplistic, but in spite of that, it provides a good foundation for what is to come. And believe it or not, no matter how advanced you get, the basic gist behind regression stays the same. It's the idea of direction and the idea of prediction. So those are the 2 things that I'm going to focus upon. Okay. So let's start off with your final exam first. And if you have any questions on the final exam, we can talk about it towards the end of the class, end of the lecture, because I'm woefully behind where I should be, but let's get to that later. So the final exam, you already have your data set, and I can give you some idea in terms of, because it's pretty much an open book exam, and again, I've given you the data set. So what you're going to get is on your data set, you will be asked to come up with 5 recommendations for the manager. When I say recommendations, they have to be specific to one of the 4 Ps. That's what, and again, I can't give you more details than this. So make sure that you look at the data and have 5 or 6 findings which are relevant to the manager, or which you can convert in a manner or form that's going to be relevant to the manager. It doesn't make a difference if your P is less than 0.05 or P is greater than 0.05. Okay, remember, P less than 0.05 allows you to tell the manager you need 2 different strategies. P greater than 0.05 tells the manager you don't need to have separate strategies for these two groups, these 2 attributes, or whatever be it. So it doesn't need to be something which is significant. I'm mentioning this again because this question might come up. I don't want this to come up during the final exam. So just make sure that you keep this in the back of your head, which is it's not something which is going to be focused on you being able to, find 5 things or 6 things or 3 things which will have a P less than 0.05. Okay? The intention is, can you convert whatever test you ran, whatever hypotheses you had, into a managerial contribution, which means one of the 4 Ps. Don't worry about the hypotheses. We are not going to care about the hypotheses. Probably, so there are going to be 2 questions. The first question is going to be completely based on the data. Okay, so I'm probably again I still don't know what the final exam is going to look like, but 2,000 words across 5 different attributes, 5 different tests that you run. So that's probably what question number 1 is going to be. Okay. Question number 2, that's an open-ended question. It could be anything. It could be on your market research process. It could be on, and again, a short answer type question. 2,000 words. No. Let's see. What is my recommendation? My recommendation is 1,000 words for the second question. So the first question is going to be worth 20 points. The second question is going to be worth 10 points. So 2,000 words and 1,000 words. It could be on any specific test. So I ask you in detail what ANOVA is about. So you explain to me in detail about that. Or I could ask you about the market research 1011 process. I could ask you about all the tests that you've run, in which case you just give me 1 sentence answers, anything at all. So that's an open-ended thing, but you will not require the data set for that, which means that if you have everything in place, you should not need to access SPSS for the finals real time. You obviously need access to SPSS, okay? So you have between today and next week to be able to work through all of that. You will get an email from the exam administrator, probably on Thursday evening, okay, which will give you all the details. But it's, I think, again, you will get the details. We still haven't finalized that. I think you will have about a total of 6 hours in which, or 5 hours, one of those two, 3 hours for the exam. You can start anytime you want in that 5-hour window, but 3 hours is what you have. It automatically turns off after 3 hours. I have not made the quiz or the final exam to last you more than 2 hours, but I'm giving you 3 hours. I think, given that there might be some infrastructural problems, probably that's the best route to go. So that's it for the final practicum, nothing over and above that. Okay. Now, what can be tested, what I'm expecting from you for the project as well as for the finals, is where we stop today. Okay. Nothing beyond class 9. Okay, but that doesn't mean you stop in class 6, but nothing beyond class 9. If you add something beyond class 9, that's cookie points. If you stop at class 9, that's fine. That's exactly where I expect you to stop, given the time that I've had. There are going to be 2 more lectures, and I'm going to apologize for this in advance, one of which I'll pre-record. One of them is actually pre-recorded, and the second one, which I'm going to record again. The reasoning behind that is, and again, whatever I can't cover, whatever I'm not covering till the end of today is going to be taken up in 3054. So even though I'm giving you all some extra lectures, that does not mean that it's not going to be covered. So 2 lectures. The first one is going to look at a little bit of multiple regression that I'm not going to be able to cover today. Okay. So what is multiple regression? We'll talk about that. That is going to be a recording from last semester. It's no use me trying to record it again. It's just useless. And the second one is what I'm going to call week 10. So week 9, so the component in the middle, I'm just going to call it week 9B. I'm not going to test you on that. If you want to go through it, because it's going to provide a very good continuation of of what you have done and where you're going to go from here. If you don't want to, that's totally up to you. Week 10, there are going to be 2 components. One is the wrap-up module, and there's going to be a little bit which is going to put all the boxes in their place, have a lovely little diagram where you should be able to put everything together in terms of where each of those tests could have been run. It might help you for your final exam, so I would suggest you download that or at least have a look at that. So those are the 2 modules that are going to be uploaded by hopefully tomorrow. One of them is a recording that I've already done, and the second one I'll probably do early tomorrow morning and update you with that. A few things on Moodle. So I should be sharing my screen. Apologies for that. Where am I?
Hello.
Yep.
Is this the multiple choice for the final practicum?
That is for the final practicum. Whatever I said was for the final practicum.
Is this still going to be multiple choice?
No, nothing is multiple choice. Everything is going to be, what do you call it? A short answer type. The first one is going to be 2,000 words, and the second one is going to be 1,000 words. So 2 questions, both of which are going to be short answer types.
Oh, okay.
Okay. All right. So let's go through your Moodle. So I'm assuming a few of you would have done the extra credit. So that's what you can see in here. So that is going to disappear tomorrow. That should have said 29th of July, but no, it'll disappear sometime tomorrow. The second one, I'm being told, is going to be online starting tomorrow, and it's going to run off next Wednesday. So you have 1 week to do that too. There's going to be 1 data set which is going to be made available to you, which has already been made available to you, which is the job satisfaction data set. And there are 3 questions that go along with that. I will have the answers. I want you to try these on your own first. I will have the answers for these online on Thursday. Okay, because I want you to try this a little bit before you have a look at the solutions. I have decided to take out the last data set, so you will not be able to see these at all. See this last data set at all. because we just don't have the time. And the final thing that's been made available is this video. I think it was made available last week, but now you will actually be able to put 2 and 2 together and figure out what's going on. Okay, so this is basically from me in terms of housekeeping issues. Any questions that you have? Anything about the final exams we can chat about later, but anything else that you want to ask? Okay, in which case let's start off from where we had stopped last time. So this data set that I've given you, which is available online, it looks at the happy productive worker paradigm. It's a very nice little story, little piece of research, which is interesting, but again, as I said, we've not had the time to go through this in detail, but I will try and cover everything that you have in here, that you see in this little slide, which is going to look at, does happiness predict production? Does productiveness affect happiness, and so on? So multiple questions on those, and I will spend a little time on this when I'm answering questions on that data set. So we had stopped at how do I get rid of this guy? Let's see. There you go. So we had stopped at correlation last time. What we are going to do is start off with regression. What was correlation? What is regression? Why are the two of them always put in together? They're very nicely related. One leads to the other. Correlation leads to regression, and regression is a refined case of correlation. We are still dealing with the same box that we have been playing around with, which is 2 continuous variables. My intention today is to finish these 2 continuous variables and then move on to, if possible, multiple continuous variables. So let's start off with that. I'm pretty sure most of you are familiar with regression equations, which is y equal to mx plus b, but we will look at it in terms of a marketing research problem today. So relating correlation and regression. What is correlation? What is regression? Correlation tells you about the relationship between 2 variables. Okay. It tells you what? First, the presence of a relationship. Second, the direction of a relationship. And third, the strength of a relationship. Regression does exactly the same thing. There is no difference in terms of what regression does, but it does one additional thing, which is what predicts out of these 2 variables, what predicts the other. You are trying to use one variable to predict another variable. That's what regression is going to be. Still 2 continuous variables, just like correlation. In correlation, you say 2 things are related. In regression, you say one variable leads to the other. So let's, before you go beyond what we are going to be looking at these tables, let me start off with an example. Okay. So the more food I eat, the fatter I get. There seems to be something relatively logical. The amount of food you eat and how fat you are related to each other. Are there other things in the picture? Do other things come into the picture? Absolutely. How good is your metabolism? How much do you exercise? There are lots of other variables that come into this relationship. I'm not going to look at them right now. Right now, I'm just looking at 2 variables. And those 2 variables are the amount of food that you eat and how much you weigh. Now, most of us would say, I think that the more you eat, the heavier you are. That seems to be a logical relationship. And what I have done in this process is that I have created a variable that is explained and a variable that explains. A variable that's explained and a variable that explains. In correlation, all I said was 2 variables were related to each other. Now I'm saying one variable explains another. Now these 2 variables are known by different names. explanator, explainee, regressor, regressant. We don't care about any of those names. We want something relatively simple, which most of you are familiar with: independent variables and dependent variables. And that's the set of terms that's used the most, not just in business, even outside of business. An independent variable is the variable which you control. Any variable that you control, business perspective, is an independent variable. How much money do I put into making my car comfortable? That is an independent variable, a variable which is under my control. And I'll give you a statistical perspective, but we start off with a business perspective because that's the most important thing that we're going to do. What about the satisfaction of the customer? Is that something that I control? Not directly. I can't control what a customer does directly. What I can do, however, is provide the customer with the best possible product, the best possible service, the best possible comfort level, the best possible speed. And as a result of those, the customer is going to become satisfied. So I don't directly control these variables. These variables are known as dependent variables. These variables are called dependent variables. A dependent variable is something which is a resulting variable. An independent variable is something that I control using the tools that I have in my hand. And what are the tools that I have in my hand? The 4 Ps. Invariably, you will go back and see the 4 Ps again and again. If I can't change the 4 Ps, I can't change anything. The only things that I can change as a business manager are the 4 Ps. Nothing over and above that. Everything happens as a result of me changing the 4 Ps. Okay. So in regression, we are going to be looking at controlling independent variables, variables which are under my control, so that variables which are not under my control, dependent variables, go in the direction that I want them to. Satisfaction, I would really want it to be high. Dissatisfaction, I would want it to be low. Positive word of mouth, I would want to be high. But I can't control positive word of mouth. It's a result of something else that I do. Independent variable, something I control. Dependent variable happens as a result of. Somebody might come to me, especially from psychology, and say, you gave me the example of eating and weight. But I think it's not eating more that leads to higher weight. I think that weighing more makes you eat more. What do I say? I actually do not have an answer to that. That could be a very valid relationship. That possibly is a very valid relationship. So this question of what leads to what? Does weight lead to more eating, or does more eating lead to higher weight? Maybe both of these are correct. Maybe only one of these is correct. Maybe one of these is correct in a given circumstance. So X and Y, which are what we call the independent and dependent variables, are something that you determine. So I'm going to get out of these slides now and go into, you still have these slides with you, so feel free to have a look at those. I'm going to go into what I like the most, which is writing stuff down. Let's write a few things down. We look at statistical conventions, number one. What do we care about them? We don't care a fig about them, but we need to know no matter what. And we are going to look at marketing conventions. X is what we call an independent variable. Let's write this down. I'm never going to write this down again after this. Independent variable, and y is known as a dependent variable. Yx, yy, y naught, z, just convention, nothing over and above that. Z means something else, z is used as something else. We usually use x and y. And all of regression goes with a simple expression, which is that the dependent variable is a function of, all it means, now this looks fancy, but all it means, the dependent variable depends upon, the dependent variable depends upon the independent variable. Now, what you see in here, it does not imply linearity. We talked about linearity last time. What was linearity? Everything was straight. And we are going to stick with that. This form, however, does not imply linearity. The linear form of this equation is what you are familiar with. This is something that you've been exposed to in high school. So the dependent variable y is equal to a certain number a plus a certain number b times x. If this is not clear right now, don't worry about it. It's going to get a little clearer. I'm assuming you haven't had a look at it since high school, so it's fine if you don't remember this. As you go along, it's going to get relatively clearer. So let's try and consider an example from our data sets. It's the best way of learning regression. Look at the data, try and figure out what's happening in that. Let us suppose I look at the variable which is importance of comfort. I say, and again, am I right in this? Am I not? I don't know. I just say, based on my perception, my intuition, my knowledge of whatever I have known for my entire life, that importance of comfort is actually a function of, notice that I'm writing F right now, I'll change that soon, is actually a function of importance of speed. Is there any logic to this argument? I don't know. This is just my intuition. The more you give importance to speed, the more importance you will give to comfort. That sounds something which might be correct, which might not be correct, but I believe that this is correct. I have my beliefs and I want to check whether or not these beliefs are true. I can do this in multiple ways, lots of fancy regression, but we start off with what is known as univariate regression, which is the easiest type of regression that you are going to see. What is a univariate regression? A univariate regression is where you have just one independent variable. Okay? I hope to be able to complete univariate regression today and move on to multivariate regression. So univariate regression is where you have just one independent variable. Now, there's something which is not written in univariate regression, but it's an implicit assumption, which is that this univariate regression is a univariate linear regression. Univariate linear regression. Okay. Now, what does a univariate regression do? It takes one independent variable and based on that tries to predict a dependent variable. Look at this question. So I said importance of speed. Is that really a variable that I control? Not really. It's not a variable that I control directly. What do I control? I think I control the engine that I put into the car. if I put an engine into the car which has a very high speed, then the importance of speed is probably going to go up. Maybe, maybe not. So this is not a very clean independent variable, but I can say that people who give high importance to speed give high importance to comfort. Why? Again, that's what my intuition is. Notice that a lot of this, is focused upon intuition. And from there, we are going to move on to not intuition, but numbers. Intuition stands in its place, numbers stand in their place. Both of those need to go together. If anything doesn't click, your ideas are not very worthwhile. However, next term or the term after that, when you move into analytics, this thing about intuition, we are going to completely disregard that. Because I no longer want to focus on theory. I no longer want to know why. Given that something is happening, can I convert it into a managerial decision? That's where the focus is going to go as we go through advanced analytics. Basic analytics, advanced analytics, and if you're in 3092, the focus is going to completely be devoid of theory, completely be devoid of intuition, and focus completely on, given that I have the results, given that the numbers tell me so, what do I do? Let's move to a new slide. I said where Y is comfort, X is speed, I am going to change this into a univariate linear equation, a univariate linear regression. Just what I showed you in the previous slide. How am I going to do this? This F is a very theoretical construct, which is why it's not very useful in marketing. It's not very useful in business. We have to start off with something which is a little bit more firm. The firm might not be correct. Whatever you think is really firm might not be correct, but it gives you a starting point. Let me ask you this before I go into this example. Ice cream. And temperature. As temperature, when the temperature is relatively high, and this is liking for ice cream, when the temperature is really high, you probably want to have a lot of ice cream. As temperatures start falling, your liking for ice cream starts falling down. But does it ever get to zero? It doesn't. It probably tapers off. Notice that this line is not a straight line. When you're looking at a line like this, or let us suppose you're looking at a line like this. Remember what they were called? Curvilinear lines. Okay. Or if you're looking at a line which is sinusoidal, let's say that. This form of the equation is all-encompassing, which means all of these lines that you see are perfectly fine. They can be captured using this equation. We want something simple. And in making that case of a simple argument, we are probably going to make a mistake. Okay. We are going to make a mistake. Linear regression is a mistake, but it's a mistake which is very close to the truth. So let's go back to, I'm going to get an eraser. See? How do I get an eraser? Okay, let me just make a new one. So let's go back to the diagram which looks at ice cream, liking, and temperature. It looked like this, a curved line. Finding a curved line is relatively difficult. So what I'm going to do is draw a straight line which is going to be a good enough representation. a representation that's good enough. Okay. And this is what we are going to study today. Not the curved line, but the straight line. The curved line is correct. The straight line gives you an answer which is good enough. As you go further, you will look for the curved lines. You will capture the curved lines. But there's a place to start, and the place to start is a simple linear combination. Now, let me come back to this before we go any further. Temperature and ice cream. Which is the explained variable? Which is the explanator? Which is the independent variable? Which is the dependent variable? In this case, it's probably easy. As temperature goes up, ice cream liking goes up. Just because you like ice cream more doesn't mean temperature is going to go up, right? I probably in this case can make a firm argument saying that increased temperatures lead to higher liking. And I can completely say just because you like ice cream more doesn't mean the temperatures are going to go up. So there are times when you know the direction of the relationship. There are times when you do not. So there's this very classic example where somebody said, when the moon comes up, the tide goes up. Absolutely true. That is absolutely correct. That's a scientific fact. But the scientific fact is also, to the minimal level, if the tide goes up, which is happening because the moon is close, okay? The moon is coming closer to us. Why? Because the mass is getting concentrated in an area. How much is the moon coming closer to us? Probably 0.0000001 meters. But the added mass of the tide leads to the moon coming closer. I know most of you, wouldn't believe this, so you can look it up. But that's how relationships happen. This is a more difficult relationship. This is a relationship which probably in everyday life you would say that doesn't hold true. But the relationship between X's and Y's is something that needs to be determined based on your intuition, based on theory, and so on. And how do we do that? I'm going to not use X and Y right now. I'm going to do something simple, which is use the actual values, which is ice cream, liking for ice cream, not lice, liking for ice cream is equal to, I'll explain these in a second, plus B times temperature. Now you're not going to see this in real life. What you're going to see is L, or instead of L ice, Y is equal to A plus BX. This is what you're usually going to see in real life. X is temperature, Y is liking for ice cream. Let's name the two of these. You will hear different names for the first one. You will hear different names for the second one. I'll give you the two most popular. Both of them are absolutely correct. The first one, intercept. Why is it called the intercept? There's logic behind it. We'll talk about that. It's also known as the constant. These are the two most popular names for this, for A. Instead of writing A, as you go into advanced statistics, you will notice it's not called A any longer. It's going to be called B0. Okay. If you ever see a B0, it means instead of writing A, we have written B0. Why is that the case? It makes representation easier, but it means exactly the same thing. The second one, it's called the estimate. It's called the slope. When you say estimate, there is something that's missing in here. Estimate is what it's called, but it should be called the parameter estimate. P-A-R-A-M-A-T-E-R. Don't worry about this. But parameter estimate is usually for an estimate for the slopes. Now, what are the two of these? Let me go back to this equation. This line that I've drawn, I'm going to draw a slightly cleaner line. Something that we can actually interpret, still ice creams and temperature. Let us suppose when I draw this line, it looks like this. I'm trying to draw a clean line, which implies that when the temperature is 0, on a scale of 1 to 7, so 7 being I like it a lot, 1 being I hate it, people still like ice cream a little. Let us say this number is 2.5. When temperature is 0, which is when x is 0, the value of y, when x is 0, the value of y is what is A. That is A. The place where the line cuts the y-axis is A. That is why it's called the intercept. It's intercepting the y-axis at the point where x is equal to 0. Now for us, what variables do we have? We have liking for comfort. We have importance of speed. We have importance of safety. They vary between 1 and 7. There is no 0. Right? There is no 0. So how do I come up with an A? You can't come up with an A because 1 and 7, there is no 0. So what we do, that should be a straight line, sorry about that. So what we do is assume that if it were possible for liking to be 0, where would this line cut the y-axis? So it's a very hypothetical concept. It's a really hypothetical concept, especially in business, because in business, as far as independent variables go, the way we measure them, zeros don't exist. In finance, they do. In marketing, just because of the way we collect data in market research, it doesn't usually exist in lower level market research. You know, as you get higher in 3090, you are going to be dealing with zeros a lot. People don't buy my product, that's a 0. How do I use it? So this is a hypothetical construct right now. If there were a 0, where would this line cut the y-axis? That's your A. That's the actual number. Once we run a few tests, we'll be able to figure out where we stand. How do you come up with this actual number? The second, 1, 7. Between 1 and 7, there's a 2, there's a 3, 4, 5, 6. If x goes up by 1 unit, if x goes up by 1 unit, y goes up, look at this graph, by a certain amount. If x goes up by 1 unit, y goes up by a certain amount. If I'm able to increase the importance of safety. How do I increase the importance of safety? I advertise talking about safety all the time, again and again and again. I keep on advertising and people start feeling that they want a car to be safe. What has Volvo done? Volvo has told people safety is an important concept. Safety is an important concept. So if you look at people who buy a Volvo, the most important thing in their mind is safety. I advertise and advertise, and if I am able to increase the perception of safety by 1 unit, from 1 to 2, the importance of speed or whatever this variable is goes up by a certain amount. This amount that it goes up by, this amount is known as the slope or B. That's what you see in here. So in a graph, when you see a linear graph, there are two components, A and B. If you have just the two of those, you can draw a straight line. You can draw a straight line and based on that, make a prediction. I'll make a small prediction in here, which is based on what I've drawn in here. Let us suppose, let's draw a new graph. Let us suppose that this is comfort, this is speed. Let us suppose that I am able to increase the importance of comfort by 1 unit, because of which the importance of safety goes up by 0.3 units. If I'm able to tell people safety is important, sorry, the other way around, right? Comfort and safety. If I'm able to tell people again and again and again that safety is important, people start saying, okay, the importance of safety is not 1, which is the minimum possible, it's actually 2, because safety is important, because Volvo has been telling us so. The importance of comfort goes up from, let's suppose the importance was 3.5, it goes up from 3.5 to 3.5 plus 3, which is 3.8. If I say, okay, I advertise so much that I can bring it up from 1 to 3, what happens to comfort now? It goes up from 3.5 plus 0.3 plus another 0.3, which is 4.1. I have made a very basic prediction. Let's make another basic prediction. What if I take it to 4? The simple answer is it goes up by another 0.3, which implies it's 4.4. So what am I doing out here? I have estimated an equation. How did I estimate an equation? We'll do that. But once I have the A and the B, all I need to do is throw in the values of X. What is X? In this case, it's safety. I throw in the value of safety. If I, as a person who is walking into the dealership, thinks that safety is a 6 out of 7, look at the prediction that I'm going to make. 6, 5, and 6, which is another 0.6, which is 4.4 plus 0.6, which is 5. If I think that the importance of safety is a 6, I am going to think that the importance of comfort is a 4.4 plus 0.6 is 5.0, sorry, is a 5. I made a prediction. It's a simple prediction, nothing big. Now, is this always going to be correct? The answer is absolutely not. It's not going to be absolutely correct. But what my regression equation tells me is that on average, that's the answer, on average, this is going to be correct. So if 10 people walk in, and each of them weighs safety at 6, the average of those 10 people is going to be close to 5 when it comes to the importance of comfort. So I'm using one variable to predict the other. Let's do something really simple to start off, because that probably is going to help us rather than just a theoretical concept. I think you have received all the theory that you need. What we'll try and do is look at an equation, run a simple regression, see how predictions can be made. Very simple. analyze regression. And we are going to do just one single thing in this class, which is linear. You meet on later on during your career, we'll be doing lots of fancy techniques, which are going to be a lot better in terms of prediction. Right now, we are doing something relatively simple, which is a linear regression. And a linear regression is really easy. All you need to do is decide what is predicting what. Once you have that, you're done. We're not going to look at any of the fancy stuff in here. We are going to look at something relatively simple. Now, I'm going to introduce to you, well, you guys would have already seen it, but we haven't played around with this. Overall satisfaction. I'm going to try and predict overall satisfaction. And that is going to be predicted using importance of safety. Sorry, house. This is the current car attribute. So how satisfied are you with the current safety levels of your car? Can I change this? Is this an independent variable? Is this an independent variable in the true sense? Yes, it is. Because how can I improve the perception of safety? By making the car more safe. How can I increase the perception of comfort? By making the car more comfortable. Powerful, speed, give them a better attribute, get a better value of the attribute, and they're going to be happier. So that's something which is under my control pretty much directly. Overall satisfaction, whether or not they are going to be happy with me overall, just because I've given them a car which has lovely styling, that doesn't mean they're going to be satisfied. It might affect their satisfaction, or it might not. But this is the setup of a simple univariate regression. How did I come up with safety results in satisfaction? I think so. That's it. That's all I have. Can I go back and look at literature and see if that is the case? Absolutely. Can I base this on my intuition? How? Because I have worked in the car industry, and I think if people think they are safe, they are satisfied with the car. So those two variables are the only ones that you need to be sure of. How do you predict satisfaction if you are controlling safety? Notice what I'm saying. What I'm saying is, if I am able to increase their satisfaction with safety, their overall satisfaction with the car is going to increase. Does it sound logical? Probably it does. But somebody might come up and say, you know, what I think is happening is that given that you are happy with your car, you are happy with all the attributes of the car. And I'm nobody to say no. That's the biggest problem with regression. And this is a problem that you're going to face always. So what is it about? This is about what is known as correlation versus causation. Let's understand what this is. Causation implies that X causes Y. And under no circumstances, unless you are running an experiment, which we are not going to look at, consumer behavior will, unless you are looking at an experiment, you cannot ever prove causation. What you are looking at in all of regression is, given that I believe this relationship to be true, I can't prove it. All I can say is, I can prove that X results in changes in Y. Changes in X result in change in Y. Now, why is, given that I'm saying that X results in Y, why can't I say X is directly resulting in a change in Y? Why can't I say that X is making Y change? There's a very good example that we can give in here. Let's look at, since we're talking about temperature. As temperature goes up, the liking for or the want for chocolates, the liking for chocolates, the liking for ice cream seems to go up. Okay. Why is it that it's happening? Is it the temperature that's leading to higher liking for ice cream? Maybe it is, but it's also possible that because of the temperature, I'm feeling hot. Temperature is making me feel hot. Given that I'm feeling hot, I want to cool down. This is what is known as thermoregulation of a body. My body wants to cool down, which is why I want ice cream. So temperature is not leading me to have more ice cream. Temperature is making me hot, because of which I'm having ice cream. So there is some other relationship that's happening. There was this story about, this is something which is used a lot in economics. So whenever you see solar flares, your crop yield goes up. The presence of solar flares are solar storms. When there's a storm on the sun, what happens? Productivity of crops goes up. That seems like a causation, but what's the logic behind it? The logic might be something which I don't know about, or it might be something I know about, which is, given that solar storms are happening, the sun makes the water come up closer to the surface of the earth because of gravitational power. As a result, most plants have more access to water. We're talking about centimeters and inches, but more plants have more access to water, because of which productivity is higher. So there is a correlation between those. The actual cause is not something that you can ever find out without running an experiment. So whatever you are going to be doing in here is correlation. I showed you the example last week, which was amount of chocolates that you eat and Nobel Prizes. The factor which is causing both of them is probably per capita income, the income of a country, how rich a country is. You will be able to predict amount of chocolates eaten based on how many Nobel Prizes have been won by your country, or you will be able to predict the amount of Nobel Prizes that have been achieved based upon the amount of chocolate that's been consumed. You can probably do both of those, but this relationship that you get, it's not a causation. This is just a correlation, because there's some other variable out there which is leading you to eat more chocolates or get more Nobel Prizes. What is it? It's income. And again, is income the sole contributor? Probably not. So whenever you run a regression, remember this, you are showing that a relationship exists. That does not mean that is the correct relationship. It's not causation. What you are proving is just a correlation. Okay? So whatever you are proving is based on the data that you see. That doesn't mean this is going to hold in every single circumstance. So this is the setup of a regression. That's all there is to it. Nothing over and above that. I've given you the details in the slides. I'm not going to look at the details in terms of the theory behind this, which I don't even think is necessary, but it's better to have it, especially since I've asked you not to buy a book. Those books are really expensive. So let's press OK. I have decided what the dependent variable is. I have decided what the independent variable is. Done. Let's press OK. There you go. That's all there is to it. A regression is done. Now, a regression has multiple components. Okay? You need to look at multiple things before you look at before you decide that there is a relationship. Remember ANOVA? This ANOVA guy is going to follow us around for the rest of our lives. If you're in market research, in fact, if you're in marketing, it's going to follow you around. First thing that you do is look at the ANOVA. What does ANOVA do? ANOVA tells you if the prediction that you made, which is Dependent variable, overall card satisfaction. Predictor, current card satisfaction. Safety. So what you tried to do was figure out if overall satisfaction with car is a function of safety. Is that relationship correct? Does it exist? So the first thing that you look at is, does the relationship exist, which is done through an ANOVA. And same thing that we are going to look at always and forever, significance. If the ANOVA is significant, a relationship exists in the direction that you predicted. A relationship exists, number one, and in the direction that you predicted, number two. If this value is greater than 0.05, no relationship exists, stop, go back home. Okay. But if this relationship is less than 0.05, then a relationship exists. Once this is done, this is a relationship present? Step one. Step two, strength of relationship. And just like in correlation, this is a relatively haphazard concept. It's a soft concept. It depends. The answer is always that it depends. And that is given to us. Remember what R was? R was correlation between the two variables. So the two variables being, in this case, overall satisfaction and safety. R square is what tells us the strength of a relationship. This is very different from correlation and is a lot more interesting. Correlation, we look at R. Regression, we look at R square. Do we look at the next one? Yes, we do. If we get the time, we'll look at that today. Otherwise, we won't. Otherwise, I'll just upload a video for you. What did R vary between? R varied between -1 and +1. R varied between -1 and +1. If R varied between +1 and -1, what will R square vary between? If I square that term, it's going to vary between 0 and 1. And hence this number, which is R square, is a percentage. Always look at R square as a percentage. You'll see lots of funny ways of interpreting R. The best way of looking at it is as a percentage. What do you mean by percentage? How is this a percentage? It's the percentage of the dependent variable explained by the independent variable. Let me give you a cleaner definition first, statistically cleaner, and then we'll give a better managerial discussion. So the actual statistical definition is the variance in Y, which is explained by the variance in X. The business definition is the amount of the dependent variable explained by the independent variable. Let's take away the variance command in there, the variance syntax in there. How much of Y is explained by X? How much of overall satisfaction is explained by comfort? How much? Percent. What's the maximum possible? 100%. Never happens. If you ever see an R square of 0, if you ever see an R square of 100, that's a problem. Those things are utopian. Neither of those can happen unless you are looking at orthogonal variables, but let's forget about those. R square is going to vary between 0 and 1. 0 implying that there is no relation. There's no way X predicts Y. 1 implies X perfectly predicts Y. Neither of those happens in real life. It falls somewhere in the middle. So let's look at this R square. What is this R square? 0.077. Now remember, a percentage is out of 100, so all I need to do is move the dot, move the decimal 2 places to the right, 7.7%. 7.7% of overall satisfaction is explained by comfort. Sorry, safety. Safety is what you're looking at. If I am able to increase the importance of safety or happiness, sorry, in this case it's the satisfaction with safety, I will be able to increase overall satisfaction. But only 7% of the change in overall satisfaction is going to happen because of the change in safety, satisfaction with safety. So that is what an R-squared tells you. What percentage of overall satisfaction is explained by safety, importance of or satisfaction with safety. Step 1, ANOVA. Step 2, R-square. Step 1, ANOVA. Step 2, R-square. Steps 3 and 4, they kind of happen together. Let's do step 3 first, but again, step 3 and step 4 do not exist in isolation, they happen together. Again, there is information in your slides which gives you a little bit of statistical detail, but you don't need to focus upon that. Step 3 is when you look at the significances of two things. The first one, remember this guy? Constant? That's A. That's the intercept. That's the constant. That's A. Remember I told you it's known by multiple names. Statistically, it's usually called the constant. Whereas if you look at other softwares, they sometimes call it the intercept. But no matter what it's called, the first one is always the intercept. I'll draw something in a minute which would probably make it a little easier. Is that significant? Yes or no? Let's have a look in here. It is. It's less than 0.05, which means it's significant. Now here is this thing about the constant. And as you get further on, there is going to be a little bit of an exception to this. We do not care about the significance of the constant. Whether or not, and this is something which stats will tell you differently, in business, please do not care about the significance of the constant. No matter what, even if your constant is not significant, it's still interpreted. You need it for interpretation. So it's very different from statistics, which will tell you, no, you shouldn't. We need to, because we need to make a prediction. Statistics is looking at a lovely model. We are looking at prediction, and you cannot make a prediction if the constant is missing. So the constant is, the significance of the constant is totally irrelevant. However, the significance of the variable is important. What did we do first? We looked at the ANOVA first. If this was not significant, we needn't go any further. If this was significant, then we looked at the model summary where we looked at R-square. What is R-square? It's the percentage of the dependent variable explained by the independent variable. Once this was done, we looked at the third thing, which was the significance of both. Question? No. Which was looking at the significance of both the constant and the B. This was A, this was B. This is the slope that we are talking about. So we've got an A, we've got a B. If the B is not significant, then whatever you have done till now goes down the trash. So your ANOVA needs to be significant and your B needs to be significant. If either of these is not significant, you don't have a regression equation. If your A is not significant, it doesn't make a difference. But if your B is not significant or your ANOVA is not significant, you do not have an equation. In this case, we have both. A is significant, B is significant as well. So now that I have this, I can write a regression equation. let's write the regression equation that you got from running this test. What was the test? The happiness or the satisfaction with safety determines the satisfaction overall with the car. Overall satisfaction is equal to a function of satisfaction with safety. Since we are doing linear regressions, we are going to write overall satisfaction is equal to A plus B times satisfaction with safety. What was A? Let's go back and have a look. A was 2.744. What was B? B was 0.374. That is our regression equation. We're done. This is a simple predictor. What is it predicting? If a person walks into my showroom and I give them a survey and they say, on a scale of 1 to 7, my satisfaction with safety with your car, the car that I bought from you, the car that I'm getting to you for getting serviced, my satisfaction is a 6. All I need to do is put this in the equation and solve it. What is it going to be? 2.744 plus 0.374 times 6. Now there's no way I'm doing this without a calculator, so let's put a calculator. Let's use a calculator. So we have 0.374 times 6 plus 2.744, which is 4.988. So a person who walks into my showroom and tells me that the satisfaction with safety is 6, their overall satisfaction is going to be 4.988. That is a simple univariate regression. I've just made a prediction based on the data that I have. But what is this regression assuming? What this regression is assuming that there is only one variable in this world which affects overall satisfaction. That is safety. That's the only thing that there is which affects overall satisfaction. Obviously, that's a very stupid, assumption to have. We shouldn't be having that assumption. But given that we have this assumption, that's your answer. That's univariate regression. Do univariate regressions exist in real life? Probably not. Do we use them anyway? Yes, we do. Why? Because of the data that are available to us. This does tell me, what does it tell me? It tells me that it is important to increase the satisfaction with safety if I want to increase the overall satisfaction with my car. What is more important in here rather than the prediction is this particular number. The B. What does the B tell you? B tells you, if I have $100 and I want to increase the perception of safety, how do I increase the perception of safety? Through advertising. I expect the returns in overall satisfaction to be a positive number, 0.374. That's an increase of 1/3 of a unit. For every 1 unit increase that I can achieve in safety, satisfaction with safety, my overall satisfaction is going to go up by 0.374. In real life, nobody's going to ask you to make a prediction based on univariate regression. We use them, but it's not for predictive purposes. What it's used for is to show the fact that increasing my independent variable is going to lead to an increase in overall satisfaction, which is my dependent variable. So that is what I am predicting. That is the most important thing that you will be predict. Now, rather than just go straight into something more complicated, I want to go through a few more of these tests so that you are comfortable. So what I did right now was predict that overall car satisfaction was a function of current safety. How satisfied you were with safety. Somebody might come and say, safety is fine, but I think comfort is a bigger driving factor. Safety is a driving factor, we found that out. But somebody comes and says, no, probably it's comfort which is a bigger driving factor. Am I anybody to say no? I'm not. So what am I going to do? I'm going to run this test too. Notice that I haven't changed anything at all. There is no reason to touch any of these. There's no reason to touch any of these. We will at a later point of time, if I get the time, touch a little bit upon this. But nothing else have I touched. What am I trying to do? Current satisfaction is a function of current comfort. Overall satisfaction is a function of current comfort. Press OK. And I have my results. We'll do 2 more of these after this, so just make sure that you are familiar with it, and then I'll tell you you have something better that you can use. Step 1. Is ANOVA significant? ANOVA is significant. So step 1 done. Step 2. R square. How much was the R square for comfort, for safety? 7%. 7.7%. How much is it for comfort? 23.2%. It explains a lot more, which means if I can get people to believe my car is comfortable, if I am able to give them that perception, they are overall going to be satisfied. Safety, not as much. Comfort, a lot more. Can I compare these two and say safety is comfort is more important than safety? No, you cannot. You cannot make a comparison across regressions, ever. Just because you have run 2 separate regressions and say one is more important than the other, no, you can't. Okay? Each regression stands by itself. Does it explain more? Yes, it does. It explains a lot more. 7% versus 23%. But is it more important? No. If I want to compare those, they have to be in the same equation, which is what we will try and do today. So step 1 done. Step 2 tells me 23.2%. Step 3. Is A significant? 0.144. No, it's not. And even if it's not, I still don't care. That number needs to be in the regression equation. That number needs to be in the regression equation, because if I make a prediction otherwise, it's going to be completely wrong. So that number needs to be there. What is more important is the second significance, which is 0.000. Is that less than 0.05? Yes, it is. So what is my equation going to be? We knew what our previous equation was going to be. This time my equation is going to be overall satisfaction is equal to 0.922 plus 0.650 comfort. Overall satisfaction is equal to 0.922 plus 0.6. I'm horrible at remembering numbers. 0.650 times comfort. According to this equation, if I'm able to increase comfort by 1 unit, the satisfaction with comfort, if I can increase that by 1 unit, how much is overall satisfaction going to increase by? 0.650 units. How much was it for safety? 0.374 units. If I make an assumption that if I have $100 and $100 increases the perception of safety and the perception of comfort by the same amount, then I can say that my bang for the buck is going to be higher for comfort. Why? because in this case, my overall satisfaction is going to go up by only 0.374 units. In this case, my overall satisfaction is going to go up by 0.650 units. So, assuming that I can increase using $100 both perception for safety and perception for comfort by an equal amount, where should my money go? My money should obviously go towards comfort and not towards safety. As an average, again as an average, there are going to be some people who are going to care a lot more about safety. There are going to be some people who are going to care a lot more about comfort, but on average, assuming no segments in the market, assuming I'm not studying any segments in the market, $100 is going to get me higher returns if I spend it on advertising comfort as compared to me advertising safety. Let's do 2 more and then we move on to slightly more complicated territories. Let's try, instead of comfort, durability. As soon as I find it, there you go, durability. Press OK. Quickly, 0.000. Step 1, yes, check. Step 2, R square, 0.306. More than even comfort. Durability seems to make a difference even higher than that of comfort. This guy's safety seems to be one of the lowest, least important factors. But we're not studying importance. Why? Because you can't compare across regression. Step 3, 0.007, 0.000. Both of them are significant. So finally, step 4, which is you write the regression equation. What is the regression equation? Overall satisfaction is equal to 1.302 plus 0.610 durability. 1.302 plus 0.6, whatever that number was, durability. One last one, so that you have enough examples to work with. Analyze regression linear. Instead of durability, let's do speed of repairs. This guy's always been a problem, right? It turns out to be non-significant, turns out to be the least important. So let's see if it at least does a little bit of its job in regression. Does it help in making any predictions at all? ANOVA, 0.468. No, it doesn't. Still a problematic case, 0.468. There's no reason for me to go any forward. I stop. There's no reason for me to look at the R square. The R square is going to be pretty much close to 0. There's no reason for me to be looking at the 2 significances. And there's absolutely no reason for me to be writing a regression equation. So this variable has always been a problem child. It's still a problem child. It just doesn't seem to be any, important in any manner or form. So this setup, where you look at one independent variable and one dependent variable, is known as a univariate regression. It's a good place to start. As I told you earlier, it's not something that is used a lot in marketing research. What is used in marketing research is what we call multiple regression. What is multiple regression? This is not multivariate regression. Again, multiple regression is a type of multivariate regression, but the term that you should be using is multiple regression. What is multiple regression? A multiple regression is where you have 2 or more independent variables. So what did we start off with? We started off with 2 categorical variables. Remember the box? From the 2 categorical variables, we went to 1 continuous and 1 categorical variable, all the t-tests. From there we moved to correlation, where we had two continuous variables. From there we moved to univariate regression, where we still had two continuous variables. In multiple regression, we have 3 or more continuous variables. 3 or more continuous variables, one of which is the dependent variable, and 2 are independent variables. 2 independent variables and 1 dependent variable. dV is equal to IV1, IV2, IV3, and so on. How many can there be? The answer is an infinite amount. But the good part about multiple regression is that instead of looking at an infinite amount, it's going to give you a small number. It's going to give you a small number. Now, usually when I go through multiple regression, what I do is I show you how to run multiple regression without what is known as an automatic SPSS filter. I'll tell you what that is, and then move on to the automatic SPSS filter. Given the time that we have, we are just going to look at an automatic filtering of variables. What does that mean? I'll tell you that in 2 seconds. Now, we have our dependent variable, which is overall satisfaction. I found out that comfort makes a difference. I found out that safety makes a difference. I found out that, one more thing, what was it? Reliability or durability makes a difference. I also found out that speed of repairs does not make a difference. I found out 4 different things. However, each of these in isolation makes a difference. What if all of them are put in together and they simultaneously try and explain overall satisfaction? Because at the end of the day, it's not one variable. When you go outside, it's the rain which affects how much you walk. It's the heat which affects how much you walk. It's your shoes which affect how much you walk. It's your clothing which affects how much you walk. There are so many things in the world which affect an overall satisfaction, a dependent variable. So what multiple regression tries to do is take all the variables that you think can affect overall satisfaction, your dependent variable. All the variables which you think can affect overall satisfaction, your dependent variable, and throw them in together. Now, is there a logic to it? It's your feeling. If you're doing proper research, not market research, if you're doing academic research, you have to give the logic behind it. You have to tell me this has been done in theory. You have to tell me, based on my observations on X, Y, and Z, I think this is a relationship that you want to study. In market research, no need for theory, you are exploring. In marketing analytics, absolutely no need for theory. We will throw in the phases of the moon if they explain sales. As long as they explain sales, I will throw that in as an explanatory variable. It's got nothing to do with theory. Given that things are happening, how can I make use of it? So what we are going to do is say that overall satisfaction is a function of the satisfaction. I can say satisfaction with speed, safety, etc., but SPSS will tell me what is relevant and what is not. So I'm going to say satisfaction with all attributes. Sorry, there shouldn't be a P in there. Which means comfort, speed, safety, speed of repairs, all of them are going to simultaneously, put everything together. All of them are going to be simultaneously affecting overall satisfaction. All of them together. And to do that, there's nothing new that you need to do. Where is my SPSS? Analyze, regression, linear. All that you need to do is throw in throw all the variables in together. That's it. So what I'm saying is all the 12 of these attributes affect current satisfaction. Now I'll let SPSS do a little bit of automation for us, cleaning out for us. This is usually not the first step that is taught in multiple regression, but we'll just make it a little easier. Look at the box in here. Method is equal to enter. Instead of enter, you make it stepwise. Enter is the default. You change it to stepwise. What does stepwise regression do? Stepwise regression first runs a regression with the first variable, the second variable, then the third variable, and all 12 of them, and checks which one gives you the maximum explanatory power. How is explanatory power calculated? R square. It checks the one which gives you maximum explanatory power, subject to a condition. What is the condition? The p-value of this needs to be significant. The p-value of this variable needs to be significant. So the variable with the highest explanatory power, assuming it's significant, is first taken on board. You're left with 11 variables. It's going to go through those 11 again and check which one explains the most. Third one, fourth one, fifth one, till it gets to the point where R square is always going to increase. R square is always going to increase. If you throw in the phases of the moon, as I said, your R square is still going to increase. But the p-value might not be significant. So the moment the p-value of a variable stops being significant, it does not take any other variable. It stops. SPSS stops at that point. All I'm going to do now is press OK, and let's have a look at the results. I pressed OK. So what did it do? The first thing it entered into the equation was durability. Why? Because durability explained the maximum R square. The second thing it imported was comfort. Why? It was the second highest. Reliability, third highest. Speed, fourth highest. Gas mileage, fifth highest. Sixth, styling. Seventh, non-polluting. Eighth, power. No ninth one. Why no ninth? Because of the 12 variables that we put in, 4 of them were non-significant. I could have done this manually, but SPSS just does it for me. SPSS just does it for me, so I am in no manner of form required to do this. So what did I find? There are 8 variables that are significant in affecting overall satisfaction. How many did we have? We have 12 attributes. Importance of 12 attributes. How many were significant? Out of those 12, only 8 were significant. 4 of them were not. 8. Look at the model summary. What does the model summary tell you? It's giving you the R square for the first equation where only one variable was entered. What was that? That was durability. R square when a second variable was entered. The first still stays. The second variable was 0.548. Just by itself, durability explains 30%. Durability and comfort put together, which are the first two, explain 54% of overall satisfaction. I throw in the third variable, it goes up to 63%. By the time I come to 80%, well, 78.5% of overall satisfaction is explained by 8 variables. 8 variables explain 80%. Imagine the amount of predictive power that I have. If I'm able to control how satisfied you are with with 8 of these attributes, I can control 80% of your overall satisfaction. Stops at 8 because the 9th one was not significant. Only till 8 are we significant. Let's go down a little further. We'll have to come back to this table. This table is really important, but we are going to stop for right now. We are going to look at number 8 because 8 is the table which is of importance to us. We want an equation with 8 variables because SPSS told us 8 was the best possible option. Is that significant? Yes, it is. So can I interpret it? Yes, you can. This is the first step, frankly speaking. Why? Because the first thing you do is look at ANOVAs. If the ANOVA is not significant, we are not going forward. But ANOVA is significant, which means I can go back and interpret this. What do I have after this? So what did it do? What did SPSS do? It ran 8 models. The first one with just durability. Why? Because durability explained the most. Significance is 0.000. Second was comfort. Comfort and durability, both 0.000. Third one, the third most important attribute in terms of explanatory power was added, was reliability. Everything is 0.000. Fourth one, 4 variables. Still 0.000. All the way till number 8. Well, not everything is 0.000, but everything is significant. Notice that everything is significant. If I take the next one, the p-value of that is not going to be significant. If I add a 9th variable to it, the p-value of that 9th variable is not going to be significant. SPSS has already checked for that. So which is our best statistical model? Our best statistical model is model number 8. What would the equation for this model be? And I'm not going to write this, and that's for a specific reason. The equation for the model is going to be overall satisfaction is equal to, it's exactly the same thing that we've done in univariate regression, minus 5.9 plus 0.444 durability plus 0.499 comfort plus 0.359 reliability plus 0.093 speed plus 0.104 mileage plus 0.128 styling plus 0.080 non-polluting plus 0.080 power. That's our big statistically correct regression equation. We are not in statistics. We are in business. So what are we going to do? A regression equation, like I told you, doesn't make too much of sense for us. We work with the parameter estimates, which are all these numbers that we see. But as a marketing research manager, it is important for me to tell the manager in as succinct, in as small, in as precise a fashion what the importance of all these variables is. So what I do, and this is known as the rule of 3, which you will not hear outside of the market research discipline. There is nothing like this in statistics. What is that rule of 3? The rule of 3 tells you that if not R square, adjusted R square. Adjusted R square is the column right next to R square. How much is the explanatory power? R square. Adjusted R square is used only to compare between various models. If adjusted R square does not increase by at least 3%, statistically it might be a good variable, but managerially it's useless, which means you can't even explain 3% of overall satisfaction. Why would I want to keep that variable? It's doing such a tiny bit. Why 3%? Again, convention. Nothing over and above that. It's just convention. Okay. Convention tells me I should be using 3%. That's something which is agreed upon by pretty much every market research company. Let's move from model number 1 to model number 2. How much is the increase? From 30.2% to 54.2%. That's an increase of 24%. So do I want to keep the second variable? Absolutely, because it's giving me more than 3%. What if I move from 2 to 3, from 54 to 62? That's 8%. Still seems to be relatively high. Why? It's above 3%. That's how I'm defining high. What if I move from 3 to 4, from 62 to 70? Still 8%. I need to keep it. Let's move from 4 to 5, 70 to 73.8. Still greater than 3. Still greater than 3. So I want to keep it. Let's move from 5 to 6. 0.738 to 0.753. That increase is less than 3%. So the sixth variable, and hence the seventh, hence the eighth, are useless for a manager. What is adjusted R-squared trying to do? Adjusted R-squared is actually penalizing you. It's actually telling you every useless variable that you throw in, I'm going to give you a penalty. It's penalizing you for variables that you have thrown in which don't explain a lot. They might be statistically significant, but they don't explain a lot, which means they mean nothing for the manager. If they mean nothing for the manager, I don't want it. Which is why I stop at 1, 2, 3, 4, 5. Model 6, 7, and 8, statistically they are valid, managerially they are invalid. So the important variable for me, the important model for me is model number 5. And I need to go and look at model number 5. That's the only one that is of importance to me. Now I have taken you through this entire process in an up and down manner, but whenever you learn a multiple regression, the first thing you do is look at, I told you ANOVA, but look at the model summary first. Figure out where you want to stop. Once you figure out where you want to stop, then go and look at the ANOVA for that particular model. So let's go in and have a look at the ANOVA for model number 5. We don't care about model number 4, we don't care about model number 8. Only about model number 5. 0.000. Which means it's significant, so I can interpret model number 5. And hence I am going to go down to model number 5, and this is the only thing of importance to me. Let me cut and paste this because this is going to be a little bit important. So what do I find to be important? Durability is important, comfort is important, reliability is important, speed is important, high gas mileage is important. There are 5 things that are important. Okay. Let's write this down. Overall satisfaction is a function of durability, comfort, please excuse my writing, reliability, speed, and gas mileage. There you go. Durability, comfort, reliability, speed, and high gas mileage. So those are the 5 things that are important to me. If I'm able to increase the perception of durability, how much is overall satisfaction going to increase by? 0.495. Which is also something you can write in front of this if you're writing the equation. I'm never going to ask you to write an equation. Nobody in marketing research is going to ask you to write an equation. In stats they will. We don't care about it. Comfort. If I'm able to increase comfort by 1 unit, how much is overall satisfaction going to increase by? 0.544. Reliability, 0.362. Speed, 0.161. High gas mileage, 0.127. So my question next is, where should I throw in my money? If I have $100, where should it go? And this is something which is non-intuitive. What I'm going to tell you is non-intuitive unless you are familiar with statistics. if you have $100, the importance is not determined based on these coefficients, these estimates that you have received. It is determined based on these numbers. What are they called? They are called unstandardized coefficients versus standardized coefficients. Unstandardized parameters versus standardized parameters. If I ask you, if I increase comfort by 1 unit, how much does overall satisfaction increase by? You look at unstandardized coefficients. If I ask you, which is the most important attribute in terms of bang for the buck, the answer is you look at standardized coefficients. Let me give you the logic again. If you don't understand it, don't worry about it. The unstandardized coefficient is adjusted based on how easy it is to move this variable. The unstandardized coefficient tells me 0.544, which means I'll get more bang for the buck for comfort as compared to durability. But it's going to be difficult to move comfort. How do I know this? Because of the variance of these numbers. Again, don't worry if you don't know this, if you don't understand this. It's going to be difficult to move this number. So what I should be looking at is these two numbers. And these two numbers tell me that if I have $100 to spend, the first $100 should go to changing durability. The order of the importance is not based on the values of the unstandardized betas, is based on the values of the standardized betas, the standardized coefficients, the standardized parameters, always. Okay? So that is how you figure out where you want to spend the money. Okay? I'll do one more example for a multiple regression and then I'll stop. We'll take questions. After that, analyze, regression, linear. Now, we've looked at current card satisfaction. What if we are looking at importance of attributes? This is not that interesting of a question. How is the overall satisfaction determined by how much importance I place upon an attribute? Somebody can come up with lots of logic for it, but I find this question to be less interesting. What it says is, if I think that something is important, I will be more, I'll have a higher satisfaction with my car. If I think that safety is important and my car is safe, I'll have a higher overall satisfaction. If I think that safety is important, given that I own a Volvo, automatically I think my overall satisfaction is high. That's the equation that I'm looking at. So what do? I just press OK. Stepwise is already checked for me. I've changed that. Make sure that you change it too. I'll press OK. How many was significant in there? 8. How many are significant in here? 1, 2, 3, 4, 5. So 5 attributes seem to be significant. How many did I throw in? I threw in 12. How many are significant? Only 5 of them. I haven't looked at the model summary though. So let's have a look at the model summary. Going from 1 to 2, that's more than a 3% increase. 43 to 48, that's more than a 3% increase. 48 to 54 is more than a 3% increase. 54 to 57 is no longer, it's a 2.5% increase because it's 0.547. So the fifth variable is managerially irrelevant. The fifth variable is managerially irrelevant. I just have to look at the fourth model. What does the fourth model say? 0.000. Perfect. So the model is interpretable. Let's look at the fourth model. What did I find when I actually ran the regression in terms of what determines overall satisfaction based on how satisfied you are with the car? We found durability. People really cared about durability. If they were satisfied with durability, overall satisfaction was high. Comfort. They cared about comfort. They cared about reliability. They cared about speed. They cared about gas mileage. However, when I asked them, what do you think is important? There are two different things. We found out what was actually important. Now I'm asking them, what do you think is important? And suddenly they're all politically correct. They're saying the most important attribute is, well, not really most, but one of the most important attributes is non-polluting. I'm being socially correct. When I actually tried to figure out whether that was important, it's not. But when it comes to saying if it's important, yes, it's important. Non-polluting is important. Comfort is important. Power is important. Reliability is important. Power. Did we find power to be important? I don't remember. But again, these are things which differ across what people say versus what people do. So let's look at the ones that are actually important, which is the order of the importance. So for the order of the importance, I should be looking at, let's do another clipping just to make sure that everything is correct rather than a lot of other useless data. What's the most important? That seems to be comfort. This is what they state. They state that comfort is important, the most important attribute. Was that true? We found it to be one of the most important attributes. They said durability being the second one. Is that what I found? Where is my mouse? There you go. Yes, durability is still an important factor. Power. Did they say power? No, power was not found to be an important predictor. But because they want to be viewed in a certain manner, I care about the power in my car. They say I care about power. Non-polluting, that's again being politically correct. This is probably socially correct, this is politically correct. I want to say I care about non-polluting car. How many of us actually look at the polluting part of a car ever when we go, the statistics behind it? Unless you are buying a Tesla, which probably you're not buying for pollution reasons anyway. You don't look at the pollution statistics. Okay, so I'll stop here. I will actually, given that I've been able to cover multiple regression, what I'm going to do is that I'm going to open up this particular data set too, okay, for you, and I'll add the questions to it and obviously the answers to it. All of this will be available to you by Thursday. Okay, so I'll stop the recording in here, and then after that, if we have any questions, because I can't go, well, I'm already over 1 hour 45, but if you have any questions, feel free to have a chat with me.
我觉得其实你在讲那3个好习惯的时候还行，然后一开头接到后面的时候也还可以，就是那儿东西那儿结束有点太突然了。但我还是没有想到我的这个问题是啥。我的标题想叫 Critical Thinking Everywhere， 但是我觉得这个可以放到 Take Home Message 里面说。就是我通过这一系列，我发现原来批判思维存在于每一个角落，而存在于任何地方，不单单是学习上。关键是如果我这个题目叫什么我怎样提高了批判思维，但是我的文章里又讲了批判思维的好处。如果我说 哦，我昨天想了，我在想我的 essay 写英文会不会太长了？